Thank you very much. Hello everyone. My name is Brandon Azad, and I'm going to be presenting Crashing to Root, How to Escape the iOS Sandbox Using Abort. First, a little bit about me. I was, until very recently, an independent security researcher, but 2 weeks ago I joined Project Zero, which is Google's applied security research team. It's kind of weird since this talk is on research that I did before joining Project Zero. So just to be clear, this talk is all about independent research. I focus my security research on macOS and iOS. I graduated from Stanford in 2016 and 2017. I was among those who discovered the original variant of the Pegasus spyware's kernel code execution vulnerability. And I also developed some open source tools, including a kernel inspection tool called memcontrol and a kernel cache analysis toolkit for IDA Pro called IDA kernel cache. Now, what got me started on this research project? It all began when I had an interesting realization while looking at a crash log on an iPhone. While scrolling through it, I was really struck by the large amount of information inside the crash log. Here you can see that this is an example crash log that includes some basic information about the crashing process, a symbolicated backtrace of the crashing thread, a dump of the thread's register state, and even a listing of what binaries were loaded at what addresses in the process's address space. So all of this really got me thinking. There seems to be a lot of processing going on to generate this crash log. Is this processing a viable attack surface? So let me give you an outline of this research project. The focus is on crash reporting on iOS, and specifically we'll be targeting iOS 11.2.6, which was the latest version available when I did this research. And our goal is threefold. We'll try to find a zero-day vulnerability. We'll use that vulnerability to escape the application sandbox, and we'll also try to elevate privileges to root. And why did I think that crash reporting was an interesting attack surface to begin with? Oh, because it seems like an absurd place to look. I mean, how can you possibly attack a system by crashing? So I figured that since I thought it was a crazy place to attack, Apple has probably not put the security auditing that this feature really deserved. So before we dive into the vulnerability, let's quickly discuss some fundamental iOS security mechanisms. iOS implements code signing, which means that all code must have a valid cryptographic signature in order to run. And the signature chain must root back to Apple. Here we've used the code sign utility to dump an application's code signature. And the part that we've highlighted here in the center shows the embedded certificate chain, where the leaf certificate at the top is my personal developer certificate. Any code without an Apple-approved signature will be immediately killed. The next security feature we need is entitlements. Entitlements are additional permissions granted to an application at the time the code is signed. Concretely, the entitlements are an XML blob that's embedded into the binary and that's protected from change by the application's code signature. Here you can see that this binary has been granted the task for PID allow entitlement, which allows it to call the task for PID system call. And we'll return to task for PID later. And the final security mechanism we need is sandboxing, which allows the system to place very fine-grained controls on the behavior of an application. All iOS apps live inside a sandbox called the container sandbox. Here's a small snippet from the container sandbox profile, written in a scheme-like language. This profile restricts which files you can access, which kernel drivers you can talk to, and even which daemons you can communicate with. So if we want to do anything interesting on the device, we absolutely need to escape the sandbox first. So now let's discuss some inter-process communication basics on iOS, and this is fundamental to understanding the vulnerability. IPC on iOS is based on Mach ports. Mach ports are reference-counted message queues maintained by the kernel. Arbitrarily many processes can send messages to the queue, but only one process can receive messages out of the queue. In userspace, Mach ports are referenced by Mach port names, which are just integers, similar to how file descriptors are references to files. Now, there's also some terminology related to Mach ports. The ability to send messages to a Mach port is called a send write, while the ability to receive messages out of a Mach port is called a receive write. Now let's talk about these messages. A Mach message is structured data that gets sent to the Mach port. It's queued in the kernel until the owner of the Mach port listens for a message. And a Mach message can contain arbitrary data, but also it can contain send and receive writes to Mach ports. This means that a send write can be transmitted to another process by embedding that send write in a Mach message that gets delivered to that process. All right, so in addition to the standard Mach ports, there are also special Mach ports in which the receive write is actually owned by the kernel itself. Chief among them are task and thread ports. A task port is a special port that can be used to control the corresponding task object. For example, calling Mach VM allocate on a task port will cause the kernel to allocate virtual memory inside the task's address space. Similarly, thread ports allow you to control an individual thread inside a task. And for example, calling thread set state on a thread port will set the values of the registers in that thread. Now, permit me to go on a brief digression for a moment. We've just talked about task ports, and task ports have a rich history of exploitation and abuse. And that's because there's a formula for how to go from holding a task port to taking control of a process. Now, the method of using a task port to take control of a process is very complicated. So I'll put up a diagram here of how the technique works. When you have a task port, you can call the functions Mach VM read and Mach VM write to directly read and write that process's memory. And then you're done. As I said, it's very complicated stuff. Apple has really put in a lot of effort to make our lives difficult right here. So obviously it's not that difficult. All things aside, it's really good to keep in mind that if you have the task port of an application, you basically have full control over it. All right, so let's get back to the background info. Now that we've talked about Mach ports, which provide IPC, let's see what daemons on iOS look like. iOS daemons are called Mach services because you communicate with them by sending and receiving Mach messages. Each Mach service is identified by a name. For example, com.apples.ca render server is the name for the core animation rendering server. And how does a client process actually gain the ability to talk with a service? Well, the launchd process, which is PID1, actually vends all the Mach services on the system to interested clients. So if a client wants to talk with a service, it'll send a message to launchd saying, hey, launchd, I want to talk with this service. And then launchd will send a reply to the original Mach message containing a send write to that service's Mach port. All right, so that's all the background information that we're going to need. As a reminder, the focus of this talk is crash reporting on iOS, and we have a three-phase goal: to find a zero-day vulnerability, to escape the sandbox, and to elevate privileges to root. Now let's look at how crash handling works on iOS. Crash handling is based on Mach exceptions, which are a generalization of BSD signals. Just like there are many types of signals, such as SIGINT and SIG-SEGV, there are many different exception conditions. For example, X-bad access is an exception that occurs on an invalid memory access, while X-crash is an exception that occurs when a process terminates abnormally. For each of these exception types, we can register a Mach port to be notified when an exception occurs. And this notification can occur at 3 levels of granularity. You can register to be notified when a particular thread generates an exception, or to be notified when any thread in a particular task generates an exception, or when any thread on the whole host generates an exception. And once an exception does occur, the kernel will send a Mach message containing details about the exception to the registered exception port. So how do you actually go about catching a Mach exception? You need to implement an exception handling service routine, which has this prototype. The exception message will contain the thread and task ports of the crashing thread, as well as other information about the exception. When this message is received, it'll be parsed by auto-generated code, and the contents will be passed to this function as parameters. The code that calls this function is auto-generated by MIG, a tool that generates Mach message parsing code. The details of MIG aren't that important. What is important is that because this function is called by MIG, there are some very important semantics around the return value. If this function returns success, then the MIG code that called this function will tell the kernel that the exception was handled and that the crashing process should be resumed. If this function returns failure, however, then the MIG code will deallocate the thread and task ports sent in the message, and then tell the kernel to try the next exception handler. These semantics are critical. So what does exception handling actually look like? Here's a hypothetical example where our process, blanket in blue, has a registered exception port for X bad access. And that port is owned by this crash handler process in red. So when blanket accesses an invalid memory address, the kernel will check its exception table and see that there is indeed a registered exception port for X bad access. The kernel will then enqueue a Mach message containing details about the exception on the port, and when the crash handler process listens on the port for new messages, it'll receive a copy of that message in user space. At this point, the crash handler process can use the task and thread ports in the message to inspect or even to fix up the crashing process. So, what does this crash handling process look like on iOS? It's a binary called reportcrash, and this one binary is responsible for running two separate Mach services, each in its own process. The first and most important is com.apple.reportcrash, which is the host-level exception handler for Xcrash exceptions. This service port receives an exception message whenever an application on the device terminates abnormally, and then reportcrash will inspect the process and generate a crash log. The other service is com.apple.reportcrash.safetynet, which is the task-level exception handler for when the first service crashes. The reason that safetynet exists is basically so that reportcrash doesn't have to handle its own exception messages. So, why is reportcrash worthy of investigation? If you start an instance of reportcrash on a jailbroken device, you'll see that it runs as root, is unsandboxed, and has the coveted task for PID allow entitlement. Task for PID allow allows you to call the task for PID system call, which returns the task port for a particular PID. And we've already seen that task port allows you to directly read and write memory in the target process, which means that you have full control over it. Thus, having the task for PID allow entitlement is basically equivalent to having full control over any process on the phone. And this level of privilege definitely warrants investigation. So, let's talk about the vulnerability. I opened reportcrash in IDA Pro and decompiled it to look at its exception handling service routine. Here's the code. This function gets called directly by the auto-generated MIG code, and the thread and task port parameters are parsed directly from the exception message. If the exception type is Xcrash, then the return value is set to kern failure, and the ports sent in the message are deallocated. Now, this is a problem because this function is called by MIG code with important semantics on the return value. Remember, if the return code is failure, the MIG code that called this function will also deallocate those Mach ports. And this is problematic because Mach ports are reference counted. So the double deallocation means that the process has one less reference on those ports than it expects, which can lead to a kind of Mach port use after free. This can result in an interesting attack called Mach service impersonation, where we effectively substitute one Mach port with another without the victim knowing. To start with, reportcrash is talking with some privileged system service. That is, reportcrash has a Mach send right to the service. Using this vulnerability, we'll try to trick reportcrash into talking with us instead. First, we will generate a malicious exception message, where the thread and the task ports in the exception message are not real thread and task ports, but instead are send rights to the Mach service reportcrash is talking to. This message would never be generated by the kernel, but because the sandbox profile allows us to talk to reportcrash directly, we can craft it and send it ourselves. Once reportcrash receives the message, it'll process it with the service routine shown earlier, and the vulnerability will be triggered. This causes the thread and task ports in the message, which are really send rights to the service, to be over-deallocated. And this will inadvertently free reportcrash's send right to the service. Reportcrash thinks that the target port still refers to the service it was just talking to, but we've used the vulnerability to drop its reference count to 0. So the port is freed, and the port name becomes available for reuse. Then, we try to get that port name reused with a send right to a port for which we hold the receive right. We generate a new Mach message containing a whole bunch of ports that we own, and then we send that to reportcrash. When reportcrash receives that message, the ports will enter reportcrash's IPC namespace, and one of them will reuse the name that originally referred to the service. At this point, reportcrash does not know that the service port was changed. Any messages that reportcrash sends that are intended for the service will instead be sent to us, allowing us to man in the middle reportcrash's connection with the service. For example, this could be useful if reportcrash tries to send its own task port to the service. That message will instead be delivered to us and giving us a copy of reportcrash's task port, and then allowing us to take control over it. Now, this is a very powerful attack, but exploitation depends on being able to find a useful service to man in the middle. And if we list out the Mach ports used by reportcrash, there really aren't any useful targets. So at this point, I had a vulnerability, but nothing useful to do with it. So I gave up. That's it. Thank you. I'm messing with you. I'm messing with you. Don't worry. The story might have ended there, but I was reversing LaunchD for some unrelated security research, and I found something quite surprising. LaunchD also implements a Mach exception handler. And guess what? It has the same bug in it. Now, I have some theories as to what development technique might have led to this, but the end result is the same. Sending an xcrash exception message to LaunchD will cause it to over-deallocate the thread and task ports. So here's the vulnerable code, but this time from LaunchD. It's very similar to the code from reportcrash, but it's not identical. Like before, the thread and task port parameters are parsed directly from the exception message. But there's also this check here on the audit token, which we'll have to bypass. Once we do bypass that check, the thread and task ports are deallocated, and then failure is returned, causing those ports to be deallocated again. Now, LaunchD is a much more promising target for an exploit. The reason is that LaunchD manages Mach ports for the whole rest of the system, which means there are many more targets for Mach port replacement. Additionally, our Mach service impersonation technique is now exponentially more powerful. Not only do we trick LaunchD into thinking that we own a service port, but since LaunchD is the Mach service authority on the phone, LaunchD will tell other processes that we own that service too. Thus, we can now impersonate Mach services against almost any other process. So how do we actually go about triggering this vulnerability? If you recall, there's a conditional check in the code that we need to bypass if we're going to trigger the bug. This thing about an audit token. This code is LaunchD checking that the exception message was really sent by the kernel and not sent by some user space process. Now this is problematic for us because the kernel will only send an exception message when a process actually crashes. And crashing our process directly will not work. Remember, the thread and task ports in the exception message must be send right to the Mach service we want to free, not real thread and task ports. So at this point, exploitability hinges entirely on one question. Can we make the kernel send a malicious exception message? The answer isn't obvious, but after some digging, I discovered that the Mach function taskSetSpecialPort can set a custom send right for the kernel to use in some situations, including, as it turns out, when the kernel generates an exception message. And conveniently, there's a parallel API threadSetSpecialPort that does the same thing for threads. So at this point, we're in business. It's actually pretty easy to trigger this bug. First, we look up the send right to the Mach service we want to free in LaunchD. Next, we register LaunchD to be our exception handler for xcrash exceptions. Then, we call taskSetSpecialPort and threadSetSpecialPort to make the kernel use the target service port in the exception message. And finally, we call abort. This triggers the kernel to send a malicious xcrash exception message to LaunchD, causing LaunchD's send right to the target service to be freed. Now all this is great, but it does beg the question, how do we keep running exploit code after calling abort? Calling abort will crash our process, and we definitely need to run more code in order to take advantage of the dangling port that we just created in launchd. Unfortunately, we can't create a subprocess using fork or POSIX spawn because these functions are disallowed by the sandbox profile. However, for a proof of concept exploit, we can get around this restriction by using a feature called app extensions to spawn another binary that's also part of our application. The app extension will crash maliciously while the main application continues running the exploit. So, how are we doing so far? We found a zero-day vulnerability in launchd, so that part of our goal is achieved. We know how to trigger the bug by crashing maliciously, and we now have an exploit primitive that uses an app extension to free Mach ports in launchd. At this point, we know that we want to use this primitive to impersonate a system service, and after that, we still need to figure out how to elevate privileges. So, let's look at the first challenge, how to use this port-freeing primitive to impersonate system services. Let's say that we're trying to impersonate some target service, so that when a new process starts up and tries to connect to this target, launchd will connect them with us instead. First, we'll use the app extension to free launchd send right to the target. Next, we generate about 500 Mach ports. Then, we use those ports to repeatedly register dummy services in launchd until the old target port name gets reused. We can check for success by asking launchd to send us the target services port. Once launchd returns one of the ports that we've created earlier, we've won. And at this point, any new process that starts up and asks launchd to talk to the target will instead be talking to us, allowing us to man in the middle its requests. So now that we can impersonate services, let's look at my first attempt to use this capability to elevate privileges. The key to using service impersonation well is in choosing the right service to impersonate. Remember, our goal is to execute code in an unsandboxed root process. Fortunately, we can look to past exploits for ideas. The Mach service impersonation technique was actually invented by Ian Beer of Project Zero as part of his Mach portal exploit. The strategy used there was to find a service to which an unsandboxed root client process would send its task port in a Mach message. Then, use the vulnerability to impersonate that service, and then trigger the client to start. The client thinks that it's talking to the original service, and so it sends us its task port, giving us full control over it. Unfortunately, Apple got wise to this, and on iOS 11, there are no longer any unsandboxed root processes that send their task ports to a Mach service. However, even though the traditional approach doesn't work, we can actually devise our own strategy by reusing what we already know. See, exception messages contain task ports, and reportcrash itself is unsandboxed and runs as root. So why not impersonate SafetyNet and then trigger a crash in reportcrash? See, reportcrash sets SafetyNet as its exception handler on launch. So if we can impersonate SafetyNet first, before reportcrash starts up, then launchd will tell reportcrash that we are SafetyNet, and so reportcrash will set us as its exception handler instead. At this point, we can force reportcrash to generate an exception, for example by sending a malformed message that causes an out-of-bounds read, and then the kernel will send us reportcrash's task port in an exception message, allowing us to execute arbitrary code. Now, this almost works, but it's not quite that easy. See, reportcrash sets SafetyNet as its exception handler for xcrash, which is not a recoverable exception type. By the time we get reportcrash's task port, reportcrash is already in process exit and will no longer be scheduled on the CPU. Thus, there's no way to use the task port that we've obtained to execute code in reportcrash. Nevertheless, even though we can't use reportcrash's task port to execute arbitrary code in reportcrash, one thing we can do is use it to steal Mach ports from reportcrash. And if we look back to the list of reportcrash's Mach ports from earlier, there's one that really stands out as being useful for exploitation, the hostpriv port. The hostpriv port is another special Mach port that's owned by the kernel, and you need to have it in order to call many important system calls. For example, the way that reportcrash registers to receive exceptions in all processes on the system is with a call to host set exception ports, and the host priv port must be the first argument. So, even though we can't execute code, we can use reportcrash's task port to steal the host priv port, which will give us access to system calls like host set exception ports. And actually, if you think about it, host set exception ports gives us a new way forward to set a new recoverable host level exception handler and then run the exploit again. So the exploit will start off the same as before. We'll impersonate safety net and crash reportcrash. Then we'll receive the exception message containing reportcrash's task port, which we'll use to extract the host priv port. Once we have host priv, we can use host set exception ports to register our own process as the new host level exception handler, but this time for a recoverable exception type like xbad access. Then we do the same exploit all over again. We trigger a bad memory access on reportcrash and receive another exception message containing reportcrash's task port. And finally, because this time it was a recoverable exception, we can fix up reportcrash and use the task port to execute arbitrary code. Now, once again, this almost works, but there's still a small problem. Extracting the host priv port from reportcrash actually works perfectly, so we do get the host priv port. However, calling host set exception ports actually fails. And the reason is that host set exception ports is actually forbidden inside the application sandbox. So, if we want to continue down this path, we do need to escape the sandbox first. All right, so how are we doing overall? We've successfully obtained the host priv port using our Mach service impersonation primitive, and we know that we want to call host set exception ports in order to complete the exploit and execute code in reportcrash. However, in order to do that, we need to escape the sandbox first. So, how will we escape the sandbox? Well, we already have this very nifty Mach service impersonation primitive, so let's try to reuse that. So once again, we need to find the right service to impersonate. This time, we can actually use the Mach portal strategy. Impersonate a service to which an unsandboxed client sends its task port. Now, this didn't work for us last time because we needed to find an unsandboxed root client process. However, this time we do not need to target a root client, just an unsandboxed one. And it turns out that those do exist. Using a brute force search, I impersonated every Mach service on the phone, and eventually found that the Druid daemon, which is responsible for handling drag and drop, sends its task port to the com.apple.ca render server service. And Druid is unsandboxed. Thus, we actually have a complete sandbox escape. Just impersonate CA render server, launch Druid, and we'll get an unsandboxed task port, allowing us to execute arbitrary code. Now, unfortunately, once again, it's not actually that easy, because Apple's added a mitigation. If you look through the source code of XNU, you'll find that there's a new mitigation in a function called task conversion eval, with a comment that says, on embedded platforms, only a platform binary can resolve the task port of another platform binary. Concretely, this means that we can't use the task port of an Apple-signed process to modify it unless our own process also bears an Apple signature. And clearly, Apple will never directly sign our exploit code. So even though we have Druid's task port, there's no way we can use this task port to modify Druid. If we go back to our diagram from earlier, Apple has effectively blocked us at this step. We can't use the task port that we've obtained with our exploit to call Mach VM read or Mach VM write, so we can't modify Druid's memory. Now, this seemed like a pretty robust mitigation, but I was way too far down the rabbit hole to give up here, so I started looking for a way to bypass it. And it turns out there's a pretty big loophole, this function task threads. Task threads returns the list of threads in a particular task, but its semantics are crucial. See, task threads takes an inspect write to a task, and inspect writes are not subject to the task conversion eval mitigation. Meanwhile, it returns a list of thread control rights for the task's threads. And the mitigation does not restrict controlling the threads of a platform binary. Thus, while it's nominally true that we can't modify Druid directly using its task port, we can call task threads to get a control right to one of Druid's threads, and then set that thread's register values directly. So if we go back to our diagram, we'll just ignore the mitigated path altogether, and instead we'll use the task port to call task threads, which is not protected, and this will give us a thread port for one of Druid's threads. Next we call thread set state, which again is not protected, at which point we now have PC control. So of course, actually doing this in practice is much more complicated, since you want to perform function calls and get return values rather than just directly setting the value of the PC register. But I wrote a library called threadexec to make controlling a process via its thread port relatively straightforward. So now we have a complete sandbox escape. First, we'll use the launchd vulnerability to impersonate CA render server. Next, we'll trigger the Druid daemon to start. Then Druid will send us its task port in a Mach message intended for CA render server. And finally, we'll use Druid's task port along with the loophole just discussed to execute arbitrary code outside the sandbox. And that gives us the complete exploit. So first, we impersonate SafetyNet, trash report crash, and extract the host proof port. Next, we impersonate CA render server, force Druid to start, and get Druid's task port. Then we combine the host proof port with unsandboxed code execution inside the Druid process to register ourselves as the host level exception handler for X bad access. Next, we trigger a bad memory access and report crash, causing us to receive report crash's task port a second time. And finally, we use this task port to execute arbitrary code. And at this point, we are now unsandboxed, root, and have task for PID. So I think it'll be a lot clearer in a graphical exploit walkthrough, so let's do that now. Here are all of the processes involved. Blanket, our attacking process, is on the bottom in blue. LaunchD is in the center. The arrows represent having send writes to the destination. Report crash is on the left with SafetyNet as its registered exception handler. And Druid is on the right talking with CA render server. So we first start our crasher app extension, which registers LaunchD as its exception handler for X crash and then crashes maliciously, causing LaunchD's send write to the target service to be freed. We now register a bunch of dummy Mach services with LaunchD until one of them reuses SafetyNet's port name, at which point LaunchD now thinks that we are SafetyNet. Now we send a message to report crash, causing it to crash, and when report crash starts up again, it's going to ask LaunchD, hey, who is SafetyNet? And LaunchD will reply that we are SafetyNet, and so report crash will register us as its exception handler. We now send another message to report crash, causing it to crash, and this time we are the registered exception handler. So we get the exception message. We then use report crash's task port to extract the host proof port, which we save for later. Next, we repeat the same attack, but this time against CA render server and Druid. We start up our crasher app extension again, which registers LaunchD as its exception handler and crashes maliciously, causing LaunchD to free its send write to CA render server. We now register a bunch of dummy Mach services with LaunchD and get the CA render server port name reused by a port that we own, at which point LaunchD now thinks that we are CA render server. We now send a message to Druid, causing it to crash, and when Druid starts up again, it'll ask LaunchD, hey, who is CA render server? And LaunchD will reply that we are CA render server. So Druid will start talking with us, and it'll send us its task port. We now take that task port and use the task threads loophole from earlier to get arbitrary code execution inside of Druid. Then we send the host proof port over to Druid, and combining the host proof port with Druid's unsandboxed code execution, we can now set ourselves as the new host level exception handler for X bad access. At this point, we repeat the first leg of the attack. We make report crash start up again and send it a message causing it to crash, and this time there is a registered exception handler for X bad access, which means that we receive the exception message with a copy of report crash's task port. And this time the exception is recoverable, so we can fix up report crash and then use the task port to take control over it. And this time, at this point, we can restore the host exception port to default And then using report crash's task for PID privileges, we can take control over launchd. And once we have control over launchd, we can fix up the ports that we messed up earlier. And then finally, we can make report crash spawn our payload binary as unsandboxed root and task for PID. And that is how you root an iPhone by crashing. So let's see a demo of how this actually works. So here, let's see, we have Xcode. I was not able to get the graphical display of the phone screen to show, but this is a live demo, and I'm going to be exploiting this phone right here. And so let's run it. Okay, so we've impersonated SafetyNet, and we're crashing report crash now. This is going to take about 10 seconds for report crash to start up again. And now we've just gotten the host priv port and started impersonating CA render server and got Druid's task port, reset the host exception handler to xbad access. And then we're going to get Druid's, we got report crash to task port a second time. And we've now spawned our payload binary, and we have a bind shell listening on port 4242. So if I go down here, and I'm going to put the mic down for a second. All right, and now we have a shell on our iPhone. And so you can see ID. So I'm root on my iPhone. I can run arbitrary commands. You can even do like debugging things. So here I'm listing out all the Mach ports used by launchd. So it's very useful as a development platform to kind of inspect what's going on in the phone. You can take control, debug any process, things like that. So it's very cool. Yeah, so let's go back to the presentation. All right, yeah, thank you. So let's talk about post-exploitation now. We've already touched on this a little bit in the walkthrough and the demo, but this is basically how I go from having report crashes task port to actually achieving our objectives. So using our code execution library, we have the ability to perform arbitrary function calls inside report crash, which again is unsandboxed, root, and task for PID allow. So what are our actual goals? Our first level goal is to use this capability to achieve native code execution with these privileges. This isn't an elevation of privileges, since we can do anything we want in report crash using ROP. However, I'm sure we'd all agree that native code execution is much nicer than writing your entire payload in ROP. So as for our second goal, I wanted to spawn a bind shell. And now when I started this project, I didn't even know if starting a bind shell on an iPhone would be possible, because all the other recent iOS exploits that had spawned a shell had needed kernel privileges in order to do so. But I wanted to see if it was possible to get a working shell without a kernel bug at all. And obviously, we just saw that in the demo that this is possible, but I'm going to walk you through how I got there. So broadly speaking, there are two techniques for getting native code execution. The first is to compile your code into a dynamic library, or dylib, and then call dlopen to load the library in the target process. The second native code execution technique is to compile your code into a Mach executable and then call execve, or POSIX spawn, to run it as its own process. Actually, though, while I was reversing launchd, I discovered a third technique for getting native code execution. And it's very similar to the POSIX spawn technique, but it takes advantage of launchd jobs. However, at the time that I discovered this technique, it was closely related to a macOS 0 day, so I decided not to use it here. So let's look at how the dlopen technique works first. We'll compile our payload into a dylib, and then mark the payload's main function with attribute constructor. This will cause our payload to be run automatically during the dylib loading process. And once we have our compiled dylib, we can use thread exec to call dlopen inside report crash, which will cause report crash to load our payload. Then the payload will run inside report crash and inherit all of its privileges. Sounds great, but if you actually try this technique in practice on the phone, you'll see the following error message. The first line says that dlopen failed, and the second shows the error message. The only important part is here at the bottom, where it says mapping process is a platform binary, but mapped file is not. This means that we're getting an error because we're trying to load our payload dilib, which is not Apple signed, into a process that is Apple signed. Now, it's possible to work around this restriction, but I decided to move on to the second approach instead. And that's the execve or POSIX-spawn technique, although we'll be focusing on POSIX-spawn. This time, we'll need to compile our payload into a standalone executable. And once we have our binary, we can call execve or POSIX-spawn from within reportcrash to load it. The resulting process will inherit reportcrash's unsandboxed root privileges, but not its entitlements. However, we can specify arbitrary entitlements ourselves in the code signature, so we'll be sure to put task for PID there. So I tried it, and I got this error message, which is not exactly the clearest error message I've ever seen, but eventually I was able to work out what was going on. The problem is that when our app is installed on the phone, the payload binary is not being marked as executable. And in fact, this actually makes a lot of sense, since under normal circumstances, an app would never be just like randomly spawning binaries that are part of its app bundle. But we're not in normal circumstances, we're writing an exploit. So the easiest thing we can do is to simply make reportcrash call chmod to set the execute permission on our payload. After we do that, we get this equally enlightening error message. This time, we do get extra hints from the device console. You'll see that there are two related entries. The first is amphd claiming that the executable was signed with invalid entitlements. And the second is the kernel. Amphi is saying that the code signature validation failed. So what's going on here? Up until this point, we've been able to avoid talking about Amphi, but we actually need to do so now. So Amphi stands for Apple Mobile File Integrity, which is the kernel extension that enforces code signing. It gets called whenever new code is about to be loaded onto the device and needs to be validated. And Amphi will kill the process if the code signature is invalid. But since doing code signature checking is really complicated and slow, Amphi actually delegates this checking to the amphd daemon in userspace. So this daemon is what actually does the work of verifying your code signatures, and so it's the component that we'll need to bypass if we're going to get our payload to spawn. Fortunately for us, there's already a rich history of amphd bypasses, and the current technique, as of iOS 10, is to use exception ports. We register our own process as the exception handler for amphd, and then we perform a data patch of amphid's memory so that when amphd tries to call the function mis validate signature and copy info, it'll crash. Then, when amphi actually does the upcall to amphd, amphd will try to call that function and then crash. We then catch amphid's exception and manually set the return value we want from that function. Then, when we resume amphd, it's going to tell the kernel that the validation in mis validate signature and copy info succeeded, and so amphd will tell the kernel that the binary is okay to run. So if we add the amphd bypass and try again, it actually works. POSIX-spawn will return a valid PID. Unfortunately, though, our code isn't actually running, and if you look at the device logs, you'll see that there's an entry noting that the kernel killed our newly spawned process for trying to call execve. And the message says only launched is allowed to spawn untrusted binaries. And the problem here is that we're running against the platform profile, which is a set of sandbox restrictions under which all processes on the system must live, even unsandboxed ones. Thus, even though reportcrash is unsandboxed and runs as root, it's still bound by the rules of the sandbox profile. And one of those rules is that only launched is allowed to spawn so-called untrusted binaries. We can bypass this restriction by simply adding the platform application entitlement to our payload, and this will make Amphi think that the binary is trusted. So if we do this, what happens when we spawn our payload now? More errors. If we check the device logs, there are now entries from container manager D and the kernel. And finally, we see that our payload was once again killed during execve, this time with a message that says failure in upcall to container manager D for a platform app. So what's going on this time is that we're bumping into another feature of sandboxing called containers. A container is a special area of the file system for a sandboxed app. Now, containers are a very interesting security feature, but the only thing we really need to know is this. The system appears to be trying to containerize our payload, which is clearly not good for us. All the errors that we're seeing are because container manager D is being blocked by the sandbox when it tries to create a container for a root process. And to make a long story short, all we need to do to avoid being placed in a container is add another entitlement, com.apple.private.security.container required, set to the value false. And once we do that, success. Our payload runs, and we can finally see its output. So we finally have native code execution with arbitrary entitlements and full privileges. And since reportcrash was able to spawn another binary with no problem, we should have no trouble getting a bash shell to work as well. All we have to do is make sure that all the binaries we want in our bash shell are signed with the same entitlements that we just saw. All right, so what are the takeaways from this presentation and this research project? First, I want to go over what we've actually achieved. Reportcrash has the task for PID allow entitlement, and as we've seen, we can use this entitlement to take control over any process on the phone. And this is basically the highest level of privilege that we can achieve without having a kernel exploit. Also, it's interesting to note that we have full user space control without having to attack the kernel at all. This means that we don't have to defeat the Apple's kernel exploit mitigations. And the kernel mitigations are improving all the time, most recently with the addition of pointer authentication on the new iPhone XS. So anytime that we can attain our goals without having to defeat these mitigations, that's a huge win. Also, the reason I started looking at crash reporting to begin with was because it was an unconventional attack surface. The traditional attack surfaces have been used in past exploits have been significantly hardened, which makes unconventional attack surfaces much more attractive to exploit developers. And many areas of the operating system have not received adequate security auditing, despite the huge risk that they pose if they're compromised. Next, we saw that Apple's task port mitigations had a serious and not previously published loophole. The mitigation attempted to prevent attackers from using a task port to execute arbitrary code in an Apple-signed process. But we found that the task threads API rendered the entire mitigation ineffective. Thus, it's always worth checking whether a new mitigation has big loopholes like this. And finally, we saw that there was a new way to obtain task for PID privileges. For a long time, processor set tasks was the de facto task for PID workaround on iOS. But Apple has recently blocked that technique. However, we've seen that host set exception ports also allows us to get the task port of a more privileged process. Thus, if we have arbitrary code execution in an unsandboxed Apple-signed binary, and we have the host priv port, and we can crash a task for PID allow process, these features are, we can combine these capabilities to execute code with task for PID privileges. And before I wrap up, there's one more thing. A new and improved way to bypass AMPD. We've already seen the traditional approach, which works by patching AMPD and catching its exceptions. In this new approach, we impersonate AMPD by directly stealing its kernel port. We implement verify code directory to directly handle the upcall from AMPD ourselves. And then finally, we use code execution inside of AMPD to make AMPD send the reply that we want back to the kernel. Since the AMPD process actually sends the reply, we still fool the kernel into thinking AMPD performed the validation. However, this approach has a few neat advantages. For one thing, it avoids the data patch, but much more importantly, it gives us access to some very interesting flags. Here's an example implementation of verify code directory using this technique. If you look carefully, the third to last line sets the isApple parameter to 1. This will give the spawned process platform privileges, effectively telling the kernel that the binary has a valid Apple signature. If we do this, we no longer need the task threads loophole, since all processes are now treated as Apple signed. In the exploit, the code that implements this technique is called amphidupe, and the big advantage of amphidupe is that it grants platform binary status to spawned processes without having any kernel bug at all, which I think is pretty awesome. And that's it. Thank you so much for listening. You can find a write-up and code on my GitHub in a project called Blanket. And also check out my blog to see explanations about the various strategies used in this exploit. So thank you very much.
ありがとうございました。